Hello, ladies, gentlemen, and in between, and welcome back to another episode of Maths with Hamblin with your beautiful host, Hamblin. And today, my boys, we're going to be looking at our second curve in the xy plane. We're going to derive the equation of a circle. A lot more exciting than a line, am I right? Anyway, let's get into it. Okay, so the first case we're going to start with is the case for a circle that has the centre at the origin, and we're going to say that this circle has a radius r. Now, similarly, when we derive the equation of a line, we're going to have to come up with an equation involving x and y that every single point x and y on the circle has to satisfy. Sounds like a hard task, but trust me, it's not. And if you're clever, here's something you'll notice. For example, consider this point here that I've made the radius touch here. And it has an x-coordinate and a y-coordinate. Now, similarly, like we did with the line, let's draw out the x and the y-coordinate as a literal length. I'm sure you'll agree, this is the x-coordinate and this is the y-coordinate. And what you'll notice, because x and y, they're perpendicular to each other, I hope you know that, but that means we've formed a right-angled triangle here, x, y, and the radius r. And we can use Pythagoras on this thing and write down that x squared plus y squared must equal the radius of the circle we're trying to find the equation of squared. And this doesn't just work when x is positive and y is positive. And because of the nature of the circle, the radius r is the same across every single point on the circle. We can draw another one here. This one has a negative x-coordinate and a positive y-coordinate. It still holds though, because when you square a negative, it's still a positive. So this side squared plus this side squared still indeed equals the radius squared. So this equation here that we've derived is in fact true for every single point on the circle. Now, isn't that just a lovely little equation? I think it looks really nice. So to recap, at every single point on the circle, we can show that its x and y coordinates and the radius of the circle form a right-angled triangle. Then we can use Pythagoras to get x squared plus y squared must equal r squared for every single point x, y on the circle. And that still holds for places where you have a negative x-coordinate and a negative y-coordinate, because when you square a negative number, you get a positive number. So Pythagoras still holds. Now, that was very simple, but the case of a circle with a centre not at the origin, that's not very fun. Anyway, let's get through with that. Okay, so now I've got to consider the more general case of a circle that does not have a centre located at the origin of the xy plane, but instead located at some general point AB. So our imaginary circle is located, has the centre located at A, B, and as always this circle has a radius of length r. Now, we can't just do the same trick we did with our last example, which was draw the right triangle and show that x squared plus y squared equals r squared. Because if you look at this actual point here with coordinates x, y, which is on the circle, then you'll notice that the x-coordinate is actually really big, and the y-coordinate is also really big, and you can see that you can't just draw a sneaky little triangle and say x squared plus y squared equals r squared anymore. So, but we can do that trick again, actually. If we draw this triangle again, then we can say that this side squared plus this side squared equals r squared. But I mean, how does that help? We do not know how to express this side or this side in terms of x and y. Because if we could express that side and that side in terms of x and y, then we could write down... Oops. So sorry, I dropped my pen. Then we could... Well, sorry, let me just start over from there. If we could find an expression for this side and this side in terms of x and y, then we could square them, add them together, and set them equal to r squared, and then we'd have an equation which relates x and y for every single point on the circle, blah, 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 blah. But I mean, how are we even going to get expressions for that? Well, if you're clever, here's something you might notice. Let's draw out this x-coordinate, like I did last time, as a literal length. So, the x-coordinate of this point on the circle, if we draw a little dotted line down, is this distance here. This whole length here is the x-coordinate. But, here's something also very clever. You want to get the distance from here to here. But how do you do that involving x? Well, if you notice, the x-coordinate of the centre point A is from here down to here. This little distance here, A. So if you take x, subtract this bit A, then you'll get the length of that little leg of the triangle. I mean, isn't that amazing? So if I just draw this triangle again down here, oh, that's probably so bad. Okay, I think that's okay. Then we've got a hypotenuse of length r. We've got one leg of length x minus A. But now we've got to figure out the next leg. We've got to figure out an expression involving, hopefully, y for this leg. Well, much similar to last time, we can draw out the y-coordinate of our point on the circle, which is y. and then we could subtract off the y coordinate of the centre point, b. And then we're left with this distance here, which you can see it's the same as the leg of the triangle, so we get y minus b. And now we've formed a triangle with side lengths we all know about, so we can use Pythagoras, and then we'll have a much similar to expression as last time, involving x and y, relating all the points in the circle with an equation, blah 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 blah. And if I just quickly rub this out, then we can write down that x minus a, one side squared, plus y minus b, one side squared, equals r squared. And you might just say, whoa, hold your horses, Jake. You haven't really proved that this is the equation of a circle located at any point AB, only really in the x and y plane. And you'd kind of be right. Well, you would be right. But, as it turns out, this equation works for a circle no matter where it is or in what quadrant, whether it's got negative x coordinates or negative y coordinates. And I'm going to have a little challenge to you. I'm going to say a challenge to you is to show why that is true. It's not too hard, it's just a little bit of geometry and just a little bit of reasoning about subtracting a negative. Hint, hint. Anyway, so, general key takeaway from this is that the equation of a circle in the xy plane with radius r and coordinates AB is x minus a squared plus y minus b squared equals r squared. So, if you ever see an equation that looks like this, where you've got like x plus 1 squared plus y minus 2 squared, you need to take the negatives of these additive terms here inside the brackets, and then you'll get the centre of the circle, which is pretty amazing. And that pretty much concludes our deriving the equation of a circle. The last thing I just want to cover is a little trick that they might do in the exam. Be sure to watch this. Now, this next part of the video is just going to show an equation of a circle that's in disguise, because they love to do this in exams and problems, is to give you the equation of a circle, but not in the form, or any of the forms that I've just shown you, in this strange form. And you might say, that does not look like anything we've seen, right? We've got x squared plus 4x plus y squared minus 8x equals 1. I mean, how is that a circle? Well, here's a little trick to show that it is a circle. We can complete the square, and I'll see what you mean. So first of all, I'm just going to complete the square of this x squared plus 4x bit. And by the way, if you've forgotten how to complete the square, you can watch the video I made about it, or you can just, look at anything else involving completing the square. Anyway, I'm not going to delve too much into the method, I'm just going to do it. So if you complete the square on x squared plus 4x, you get that this bit, x squared plus 4x, is the exact same thing as x plus 2 all squared minus 4. If you don't believe me, just expand this out and you'll get x squared plus 4x. And then this y squared minus 8x will be written as plus, I'm going to do it on the next bit, that's y minus 4 squared and minus 16. If you don't believe me again, just expand it out and you'll get that. And that's still equal to 1 because we haven't really actually changed anything. And then, I'm sure you can see where this is going, we just add 16 and 4 to both sides, and we finally get that x plus 2 squared plus y minus 4 squared equals 21. And there you go. So then you can identify that this equation is actually the equation of a circle at centre negative 2, 4, with radius root 21. Because remember, this equals the radius squared, so you need to square root this to get the radius. And remember, you need to negative these numbers here to get the centre. Anyway, that's pretty much it for this video. That's everything you need to know about the equation of a circle and how to derive it. And next episode will be about problems involving circles like this. It's going to be a real fun ride. Anyway, I hope you enjoyed this video, and thank you very much for watching Maths with Hamblin. Till next time.